Temperature. Temperature is a measure of the average kinetic energy of the individual particles in the sample. At a warmer temperature, the particles are moving faster and they have more energy. At a lower temperature, they have less energy. And I have an analogy for this. I live in Reedley because I hope you've at least heard of Reedley, right? Did you know that Reedley has a beach? We do. We have a beach. It's on the Kings River, but it's a beach. It's a big sandy beach. Right now there's hardly any water, but there's lots of sand. So imagine people at Reedley Beach in August walking barefoot on the sand. The sand is hot in August, isn't it? Hot sand, are the people strolling along? No, we would say they're hot-footing it to the water, right? They're going quickly. Hot things, the particles are moving quickly. If you go to Pismo, it's cold there in the summer and foggy and overcast, which is why people go there, right? Because we want to get out of this heat and the incessant sunshine. So there the sand is cold and wet and barefoot people just strolling along. Cool temperatures, particles moving slowly. Okay, so that's kind of a qualitative thing. Of course, we have to measure and quantify everything, don't we? So there are 3 temperature scales, and all of these show up in chemistry, so we need to talk about them. You are probably most familiar with the Fahrenheit scale. This is what we use when we talk about what temperature to bake the cake at or what the loaf for tonight is going to be. On the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and boils at 212. Just based on those numbers, would you guess that this is metric or English? English. This is a typical English system unit with odd numbers in it, just kind of seemingly random. Room temperature is about 72. We're familiar with those things. The Celsius scale has sometimes been called the centigrade scale because it's based on 100. Water freezes at 0 and it boils at 100 degrees, and those are important temperatures to know. Water freezes at 0 and boils at 100. And then room temperature is going to be around 22 degrees Celsius, just to kind of have an idea of what that means. And then we also use the Kelvin scale. And the Kelvin scale is important because it avoids negative temperatures by assigning 0 Kelvin, which looks a lot like OK, but that's a 0. By assigning 0 Kelvin to the coldest temperature possible, which we call absolute 0. Absolute 0 is the temperature at which molecular motion essentially ceases. And there are groups of scientists trying to get something that cold, and nobody's quite gotten there. I think they've gotten very close, but nobody's gotten to absolute 0 just yet. Scientists like to try to do the impossible. So we need to use the Kelvin scale whenever we talk about gases. And so that's why we need to learn about that. So when we look at a comparison of thermometers measured, marked in these different scales, here's the freezing point of water, 32, 0, and for Kelvin it's going to be 273.15. Boiling point, 212, 100, and 375.15. 373, sorry. So between the freezing and boiling point of water on the Fahrenheit scale, there's 180 degrees, and on the Celsius scale, there's 100 degrees. This is a nice metric unit. It has to do with hundreds. The Kelvin scale, these, by the way, these are not degrees Kelvin, they're just kelvins. So 100 kelvins, 100 Celsius degrees. A Celsius degree and a Kelvin are the same size, but it's just offset. 0 is in a different place. So there are equations to help us convert between these. And these are things you're going to need to memorize for Chem 1A. So you might as well memorize them now, right? So you need to memorize these. So converting those are backwards. You don't know how that happened. So if we want to convert Celsius to Fahrenheit, then Fahrenheit will equal Celsius times 180 over 100 plus 32. To convert Fahrenheit to Celsius, we'll take the Fahrenheit temperature minus 32 and then multiply by 100 over 180. So these are the two that are hard to remember. The Celsius to Kelvin conversion is much simpler because it's just an offset. And so the Kelvin equals degrees Celsius plus 273. For significant figures, these calculations mix addition or subtraction with multiplication and division. The 100 and the 180 and the 32 are all considered to be exact numbers, but it still gets messy. And so this is a much easier way to do Sig Figs for temperatures. Keep the same number of decimal places. If you've got a Celsius temperature that's 29.4, you've got 1 decimal place. When you convert it to Fahrenheit, round it to 1 decimal place. Okay, so we'll do some examples. Body temperature is 98.6 degrees Fahrenheit. What is body temperature in Celsius? Well, let's go back and look at that equation, right? So we want Celsius. Celsius is Fahrenheit minus 32 times 100 over 180. So degrees Celsius is degrees Fahrenheit minus 32 times 100 degrees Celsius over 180 degrees Fahrenheit. This textbook uses a slightly different approach with these equations, and I think it's a lot better because most of the books don't put any units into this equation. When we put the units in here, that helps us to figure out what the equation is, because if we've got a Fahrenheit temperature, we want to subtract 32 so that our zeros line up. And then there's 100 Celsius degrees for every 180 Fahrenheit degrees. And we're going to put Fahrenheit on the bottom so that the Fahrenheit unit cancels out and we get degrees Celsius. So if you're good with equations and units, you can reason it out. If what I just said about the units didn't make any sense to you, just memorize it. Okay, that'll work just fine. So we want to take this number and plug it into this equation. So we've got 98.6 degrees Fahrenheit minus 32 times 100 degrees Celsius over 180 degrees Fahrenheit. And your calculator is usually pretty good with order of operations, so it'll be okay. Minus 32. No, it's not going to be okay. What I'm doing is I'm watching my calculator, and yours may be different, but I put in 98.6 minus 32. If I press times, it does not do the subtraction. It needs to finish the subtraction, and so I need to press the equal sign so that it finishes this before I multiply. Otherwise, I'm going to get 98 minus 32 times this, and that's not what I want. Times 100 divided by 1.8. Oh, not 1.8, divided by, I'm like, wow, that's really high. Divided by 180. And my calculator gives me 37. How many decimal places did I start with? I have one. I call the things to the right the decimal place. So this goes to the nearest tenth, right? This number should also go to the nearest tenth, because of that shortcut that I told you for units, for temperature units. So we should report this as 37.0 degrees Celsius. That happens sometimes. There's a significant zero at the end of your number, and your calculator won't do it for you. Yes?
So it's always the significant figures or decimal places of temperature sorted out.
Right. The temperature you're starting with. So I'm converting 98.6. This is to the nearest tenth, and so this will also be to the nearest tenth. And one of the reasons for that is that a Celsius degree and a Fahrenheit degree are very close in size. They're less than 2, a factor of 2, different. And if it was a factor of 10 different, then we would be more concerned. But we don't want to have to think about all the Sig Figs in there. And sometimes it ends up playing tricks on us anyway, and so this really works the best. If your starting temperature is to the nearest 1 degree, then your answer is to the nearest 1. Starting to the nearest hundredths, then answer to the nearest hundredths. The number of significant figures might change. It might not be the same number of Sig Figs. Okay? So any questions about getting 37? Yes?
So it's not like
It's looking at the number of decimal places in this one. Here it ended up being 3 and 3, but let me show you what happens if we do 102.5 degrees Fahrenheit. Somebody's got a high fever, right? Well, that's a loud train. So 102.5 minus 32 equals times 100 divided by 180. So now my calculator is showing me 39.1666, repeating forever. This is to the nearest tenth. I should report this to the nearest tenth of a degree. So I should call this 39.2 degrees Celsius. How many significant figures did my first number have? It had 4. And this one only has 3. So you can't go on number of Sig Figs. You go on the uncertainty, or the number of decimal places. The place where the last digit is. The uncertainty is in the tenths. I'm going to keep the uncertainty in the tenths. So that was an aside. What is this temperature in kelvins? Well, the Kelvin temperature is equal to the Celsius temperature plus 273. So the Celsius temperature is 37.0. We add 273. And we get, my calculator shows 310. We need to add 0.0 Kelvin. Because this was measured on a thermometer that gave us information to the nearest tenth of a degree. And so when we report this answer, we don't want to call it 310 and imply that we're only guessing to the nearest 10 degrees, right? We want our answer to reflect the measurement that was made, even when we're converting units. Any questions? Yes?
So when doing temperature problems, you don't count Sig Figs, just decimal places, right?
You count decimal places. Yeah, and if you want, I can show you why that is. Do you want to see it?
Sure.
Okay, so let's just look at this one and do the whole Sig Fig thing, right? So 98.6 minus 32. 98.6 minus 32 equals. Okay, so that would have an intermediate value in here of 66.6. These other numbers in the temperature conversion are exact. So when I take 98.6 and I subtract an exact number, the uncertainty is going to be the same. And so this is still the last significant figure. And then I'm going to take that, I'm going to multiply by 100, and I'm going to divide by 180, and those are both exact. And so my answer should have the uncertainty in the 10th place because this is 3 sig figs, and that will be 3 sig figs. Okay? There are a few places, and this is an example of one of them, where the rules for significant figures don't line up with common sense. Because when we do this guy, no, actually that one's going to be okay. Never mind. There are places where if you strictly follow the rules for sig figs, you'll get something different, but it's not good. So this is much easier to say, here I've got 1 decimal place, I end up with 1 decimal place. Okay? I'm sorry for all that stuff in there, that was probably confusing. You guys want to see another unit temperature conversion, or are you good with this? Yes, is like this, or no? Yes? Okay. Let's do this one. What temperature in Fahrenheit is 630 Kelvin? Do we have an equation that relates Fahrenheit and Kelvin? No, we don't. What can we do? Kelvin to Celsius, and then Celsius to Fahrenheit. So we're going to first convert our Kelvin temperature to Celsius. So the equation was Kelvin equals degrees Celsius plus 273. We need to switch that around. So if we subtract 273 from both sides, then over here we have Kelvin minus 273 is equal to degrees Celsius. Okay? And so the Celsius temperature will be the 630 Kelvin minus 273. 630 minus 273 equals. Calculator says 357 Celsius. Now we need to take that and convert it to Fahrenheit. I'm going to write the Fahrenheit equation up here. Degrees Fahrenheit, I'm blanking, is degrees Celsius times 180 degrees Fahrenheit over 100 degrees Celsius plus 32. Wow, I saved that barely. Not 37, 32 degrees Fahrenheit. So those of you with notes, did I do that right? I was figuring that out in my head because that's how I do them. I don't have them memorized. I just reason them out every time. Or I use the app on my phone, right? Okay. So we need to plug the 357 into here. So degrees Fahrenheit will be 357 degrees Celsius times 180 Fahrenheit over 180 Celsius, 100 Celsius. And then we have to add 32 because the Fahrenheit scale is offset by 32 degrees. 357 times 180 over 100 plus 32, 674.6 degrees Fahrenheit. What about sig figs? Well, we need to look at which place the uncertainty is in. The 630, that's not a well-written number. Where do we have to assume the uncertainty is? In the 3, actually. We have to assume that 0 is just holding a place. So this tells us that this was measured to the nearest 10 degrees, and so the Fahrenheit should be to the nearest 10 degrees. So we can be sloppy like they were and call this 670 degrees Fahrenheit. Or we could say 6.7 times 10 to the 2 degrees Fahrenheit. Any questions? So sometimes you have to use two different equations. It happens more in this chapter, this part of the course, where we're trying to make sure you know how to do temperature conversions, but usually it doesn't happen later on.